Section 1.5 is shifting, reflecting, and stretching graphs. Before we look at this section, we need to look at what are called parent functions. So in this unit, we're going to be shifting, reflecting, and stretching graphs. So it's essential that you understand the basic shape of the graph before you perform any of these transformations. So all these changes are called transformations. You can perform one, you can perform two, you can perform a whole combination. Order does matter. We're going to talk about that. But if you know your parent functions, it's going to be easier. So if you look, our linear function, which we've all seen before, is just a straight line, right? So that's why you look at the slope, you look at the y-intercept. Here's the function right here, y equals x. Okay, remember f of x is just another way to say y. It's just the function evaluated at x. It's also called y. Okay, absolute value is a v function, so f of x is equal to the absolute value of x. Our square root function looks like half of a parabola on its side. Remember, we couldn't have this other half of the parabola here, or it wouldn't pass the vertical line test. It wouldn't be a function. So our square root function looks like that. It stops at 0, right? You can't take the square root of a negative number and have it be a real number. Our quadratic function, your parabola, looks like a u always. And what's determining this is the squared here. That quadratic, the second power makes it a parabola. A cubic function, which looks kind of like a squiggle, and then our rational function, which I told you we're going to get into those a little later in the year. You're going to learn how to determine asymptotes and everything like that. But the rational function has asymptotes, so that's why it looks a little funky. These two pieces are actually your function, and that happens when you're looking at f of x is equal to 1 over x, where x is in the denominator. Okay, so those are your parent functions. We're going to be looking mostly at a quadratic, so parabolas. First transformation is called a vertical or horizontal shift, meaning moving the graph up or down, left or right. So literally just picking it up and shifting it. So given the graph y equals f of x, so a function, shifts are represented by, if it's vertical, it's tacked on the end. So this right here represents my shift. If it's a plus, it moves up. If it's a negative, it moves down. The vertical shift you take as it is. You'll notice the horizontal shift is a little different. So horizontal shift to the right, you might be thinking positive direction, but actually the negative represents a shift to the right, and a positive represents a shift to the left. So these ones, just make a note, these ones are a little trickier. It's the opposite of what you think it would be. Whereas vertical, we're talking, take it as it is. So if you saw this, h of x, a function, is equal to x squared plus 2, I would say, well, the parent function here, without any transformations, would just be a plain old parabola. So my parent function, I'm going to label as g of x is equal to x squared. Just a plain old parabola without any transformations. Hits at the vertex, hits at the points 1, 1, negative 1, 1, 2, 4. I'm just doing this so that we have a little bit of a rough sketch here. There's my parent function. So I'm going to label this g of x, the parent function. Now this plus 2 on the end outside of the squared piece is a vertical shift up 2 units. So I could take this graph that I have here, copy it, paste it, and literally just move it up 1, 2 units, and now I'm looking at the transformed graph, h of x. So this one, the pink one, I'm going to draw an arrow here and label it h of x. It's really that simple. It's just a matter of decoding the transformation. So it's essential that you know the parent functions and then that you can decode the transformation. So x squared plus 2 up 2 units. So the blue here is the parent, the pink is my transformed. So I was looking at these, finding equations from the graph. This first one, it's sitting right on the vertex. They tell me that's my parent function, f of x equals x squared. The next one I realize has been shifted up 1, 2, 3, 4 units. That means this function, which they're calling g of x, so I'm going to call it g of x, is equal to a vertical shift is something you tack on the end. So I just write plain old x squared, and I moved it up 4, so plus 4. The next one is a little trickier. There's 2 transformations. So normally I would have started at the vertex. I would have started right there. But I went over 1, 2. I went 2 to the left. And I also went down 1. So I'm going to write, they called this one h of x. And our horizontal shift happens inside the squared function. And remember, it's the opposite of what you think it is. So even though we went to the left 2 to the negative direction 2, I show that by doing a plus 2. And then I went down 1, and that is what you think it is. Tack it on the end, so minus 1. And that's my equation for that function. It's going to come with practice. It's going to come with time. The more you do, the more familiar you are with the parent functions and the transformations, the easier it's going to be. You can save yourself a lot of time in terms of graphing a nice sketch of a graph if you know what a parent function is and how to decode the transformations. The next transformation we see is reflecting a graph. So you can reflect a graph. We essentially just look at its mirror image of the graph flipped over a line. The transformations we're going to look at are when it's flipped over an axis. So reflection in the x-axis, reflection in the y-axis. So if you reflect in the x-axis, you negate the entire function. You're negating the y. If you transform or reflect, over the y-axis, you just put the negative on the x. So notice the difference of just the x versus, this is just the x, versus a negative on the entire function. Okay. In order to find these, you really have to look at, you're going to be looking for graphs that are upside down. So if it's a reflected graph, it's upside down. Okay. So here it looks like it has 2 transformations that happen to it. Our parent in this case, since it's a parabola, was x squared. I'll call it f of x. So in this case, the parent would have looked like this. And it looks like it went reflected over the x-axis here and then was shifted up 2 units. So my function here is g of x, and to show a reflection over the x-axis, I negate the entire thing, so negative x squared plus a 2 on the end. Okay, so the next one we're looking at, the parent would have been over here, so it was definitely shifted 1, 2, 3 units to the right and then reflected over the x-axis. So I would write this as, we'll call this one h of x is equal to the shift to the right goes inside, so x minus 3, because it's the opposite, and then I put a negative out front. So this whole final function would end up being h of x is equal to negative x minus 3 squared. So I'm going to do some examples. We're going to look at different transformations, but I'm going to start with the parent function of f of x equals the square root of x, which you saw up in your parent function chart, but I just want to sketch roughly another parent function for us. And it's going to look like this. Remember, it's not going to go past the point 0, 0. It's going to go to 1, 1, and then at 4, 2. So it's half of a parabola on its side. That's the function right there, part of it. It's going to keep going. There's an arrow on the right, but there is not an arrow on the left. This is my final point. That's it. It doesn't go beyond that, or it's not going to be a function. So when we look at the transformations we're doing, we look at g of x is equal to negative x squared. Or I'm sorry, negative square root of x. So this right here tells me this was a reflection over the x-axis. So reflect over x. So here's how I'm going to draw this. I draw my parent. Which I'm actually just going to copy from up here. And so my transformed is going to look like this. Reflect. You want the mirror image. So this is g of x. It's my transformed one, whereas this is my parent. The next one, the negative, is on the inside of the function. So this is actually reflect over y. So here's what this one would look like. I'm going to draw my graph in the middle so it's a little easier to see. I need to have room to reflect over y. My parent function, very rough sketch, would look like this. I'm going to call it p of x as my parent. And then h of x would be the mirror image over the y-axis. So there's h of x, my parent function the other way. K of x, what do you think the two transformations that are happening here are? First thing we see is this negative out front, which tells me that I'm reflecting over the x-axis. And then I also realize there's this +2 on the inside. So this out here tells me reflect over x. And this on the inside tells me shift left 2. Remember, it's the opposite when it's on the inside. So I'm going to draw my parent function, something like that. I move it left 2, and then I reflect it over the x-axis. So if I moved it left 2, it would look like, this, left 2, but then I reflect it, so ultimately it's going to look like this, and this ends up being k of x, my final, where the purple one was p of x, my parent. So notice the shape is still the same, the general shape. I haven't changed the shape. I just moved the graph around. I shifted it left, right, or reflected it. Because the next type of transformation we're getting into are called non-rigid transformations. So horizontal shifts, vertical shifts, and reflections are all called rigid transformations because the basic shape does not change. However, there are non-rigid transformations, meaning the shape of the graph gets a little distorted. So these include horizontal stretches, shrinks, vertical stretches and shrinks. And those are the ones we're going to hit in this class for Algebra 2. So a horizontal stretch or shrink, horizontal axis, we're talking the x values, whereas a vertical stretch or shrink, we're talking the y values. So for the function g of x equals c of f of x. So this is our transformation right here when we're talking about a vertical stretch or shrink. We say it's a vertical stretch when c is greater than 1, so any number bigger than 1, so 7 or 3 or 4, okay? If it was a -3, it would be two transformations put together. The negative would be a reflection, and the 3 would be a vertical stretch. A vertical shrink is when c is between 0 and 1. Okay, it's not going to be 0 because 0 times the function is going to make the whole thing 0. It's not going to be 1 because that wouldn't change the graph. So we're talking about any fractional value basically between 0 and 1, so a half or a third or 3/4 or 2/5, something between 0 and 1. So here are some examples. This is an absolute value function, and you can see here's the parent right here, and then they show a vertical stretch. We multiplied by a number bigger than 1 out front. The 3 made the graph tall and skinny. It pulled the graph upwards vertically. Imagine the x-axis stays the same and the y-axis gets pulled up. And then you notice over here, this is my parent function. And we multiplied by a number between 0 and 1, a third, and the graph got shortened. It got short and fat. Imagine if it was being crunched, right? Crunched down in a compressor. Vertically, horizontally it's staying the same, but vertically it's changing. It's kind of difficult to determine. We're mostly only working with vertical stretches and shrinks. So a number bigger than 1 makes the graph tall and skinny. A number between 0 and 1 makes it short and fat. We are going to look at how to apply all these transformations and what they're going to do to our graphs and what order we need to do them in class.